Great. Okay. Welcome everyone to this edition of HIT seminar. Today, we are really glad to have Giuliano Giacalone. I'm sorry, I still cannot get it right.
That was good.
Yeah, and Giuliano, got his bachelor degree from University of Rome, but after that he went to Paris and then essentially got his PhD from Saclay, and in 2020. So since the end of 2020, and until now he's a postdoc fellow at the University of Heidelberg, and recently he has really done a lot of work on sort of initial condition versus the fluctuation and correlation in heavy ion interactions. So today he will give us talk about initial state of quark-gluon plasma and then its status and connections. Please go ahead, and Giuliano.
Okay, all right. Thank you very much for the introduction and the invitation. So indeed, this talk is about initial state of quark-gluon plasma. So I thought it was nice to give a sort of review of where we are there, and also how now it's getting linked with other topics in nuclear physics, which I think is very exciting. So this talk is, I will just review a quick review about heavy ion collisions in QGP, and the way we probe the initial state of quark-gluon plasma from data, so how to relate final state quantities to initial state ones, and we'll discuss in particular the most powerful probes, I believe, which are therein coefficients, mean transverse momentum, and the focus of this talk is on mean transverse momentum flow coefficient correlations, which open a lot of possibilities. And then I will then discuss what kind of frontiers of the physics of the initial state you can probe with these observables. And since this is actually a big topic. This cannot be covered in one seminar, or unless you put really a reasonable number of topics in it. But since this is the hadron IoT, I thought it would be nice to give an overview of what is the frontiers in terms of hadronic and nuclear physics, which goes in the modeling of the initial state of nuclear collisions, of which you can probe with these observables. So hopefully this will work out. And the topics will be in particular the size of nucleons. We have the recent paper on this published in PRL, and also another paper published in PRL about the role of intrinsic nuclear shapes, which is something which I've worked with a bit. So just briefly, heavy ion collisions is the idea of performing an experiment where you collide nuclei at the highest possible energies. So by doing so, you do high energy physics essentially, but you probe emergent phenomena. So you go in a regime where, if you want, particle densities are unprecedentedly large. The interaction region of a heavy ion collision is a huge particle density, quantum energy densities, much larger than ordinary nuclear matter, and so you probe sort of a new phase of if you want, strongly interacting matter. And what you're after are in particular emergent phenomena, collective descriptions, which emerge in this kind of context. So this is something that you see in the data almost by eye, if you want. You may be familiar with these pictures, even if I don't have, which are essentially histograms of pairs of particles as function of angles in the detector and recorded in high energy nuclear collisions. And you see the emergence of global patterns, collective effects, which hint to a collective description of the underlying physics, the underlying system created in the collision, and this is what you want to probe. So it's emerging phenomena in high energy physics, which is what we can do with heavy ion collisions. What happens is now very well established. So, sort of summarized here, you have a system which is so dense of the interaction of two nuclei, which you can at least, I will be discussing here mostly large systems at the highest possible energies, such that you have a system which eventually you can approximate it with the sort of the reaching of local thermal equilibrium, which occurs around the time scale of QCD, so 1 per megahertz. That's typically the time scale. So it's a very short time scale, which the important thing is that it's much shorter than the actual size of the system. And then this is why your effective description in terms of relativistic fluid works well. So what you do is basically that you have a system which is as big as a nucleus, so length scales of order of like 10 Fermi, but you can describe it effectively with macroscopic concepts like energy densities, pressure, velocity fields, and so on. And there's also, we know that this is a quasi-ideal fluid, but there are also transport properties. There are viscous corrections. So the main goal of these experiments is to extract these quantities which are coming from the microscopic dynamics. And the evolution is basically that of a that of a cosmological model, if you want. You have a conservation of energy momentum encoded in these quantities and so on. So the picture is really this: you collide a bunch of nucleons, which eventually turn in a short time scale into a quark-gluon plasma. And we call it a quark-gluon plasma. The feature that's most characteristic of it is the equation of state, if you want, which is something that you can get from QCD at high temperature. And this is the peculiar feature is the large number of degrees of freedom, which is the fact that you have quarks and gluons no longer confined in hadron, color degrees of freedom active. This is what we call the QGP. The QGP, of course, we do not see it directly in detectors, right? So all we see is a spectrum of particles. So what does it mean? That if you go along the temporal evolution of the heavy ion collision, so you start with Lorentz contracted nuclei, then there is a quick phase of equilibration, and then the QGP phase sets in, which will last for typically 10 Fermi Rc for a central ion-ion collision, and this will then cool, expand and cool, and then turn into hadrons again. What you see at time equal infinity is just hadrons, so it's a spectrum in momentum space. This is the picture really, and in this talk, what I'm interested in are initial stages. So initial stages is typically that phase which comes from which covers the interacting nuclei up to the time where you start to have a QGP. Okay. Of course, the difficulty is that again you have to somehow reconstruct everything from the spectrum at infinity. And all you can do is building observables to assess the initial stages. And observables are, as you will see, you can actually do this. It's not a problem. You can actually sort of see the initial state from the observables, but if you use the right one. The one which I will use, which are some of the most basic eventually, are like the number of particles, which is the density of the spectrum, the anisotropies of the spectrum. This maybe you perhaps know the flow coefficients. So the Fourier harmonics of the azimuthal distribution in the transverse plane, and also very important is the average transverse momentum of these particles, which is the energy per particle. And we'll see that too. So you have to the idea is to reconstruct initial stage from these observables. So how do you do this? So first of all, I will discuss about flow coefficients. Again, the idea is that you have a lot of hadrons which are recorded in a collision event. Question that you want to answer is this distribution along phi as isotropic? This is something that, of course, you don't see much from just one event, one picture. If you do a careful study, and you will be able to experiment with this, know how to do this. You can extract the Fourier harmonics of the azimuthal distribution. These are called anisotropic flow coefficients, and this is important problem with QGP. So why measuring these anisotropies is like assessing the initial condition eventually. The point is that hydrodynamics is sort of very simple. It's a sort of deterministic in its function. The initial condition determines the flow. Basically, that's it. There's no huge correction on top of that, if you want. So anisotropic flow, or just the flow of the fluid, is governed by a force, which is given by a pressure gradient. Okay, this is the ideal fluid. And what happens in a heavy ion collisions usually is that there is a strong second harmonic, which is called elliptic flow, for the following reason: that as you have nuclei which are overlapping at some impact parameter, so they're sort of displaced, you generate this elliptical interaction region. The force in a medium which carries such anisotropy in an coordinate space is not isotropic, so there is an imbalance of pressures, which means that after some evolution, if you look at the momentum space or the flow, the momentum space, or like how the momentum is distributed in your medium, this shape will be converted into something like this, where you see the anisotropy now is along x or px, and if you then look at the modulation of this according to the momentum space angle, there is a cos to phi, and this is what defines the elliptic flow. So geometry turn in the initial condition turns into the anisotropic geometry in the initial condition turns into anisotropy in the momentum space distribution. This generalizes. This is something very known very well, in the sense that QGP is not a smooth object which has only this intrinsic elliptical shape, but there are fluctuations, energy density fluctuations, and so you can have any multiples non-zero. So all deformations are sort of contributing to this shape. They are typically quantified by units of eccentricities, which are precisely multiple moments in 2 dimensions of the energy density of the system. And as long as you have a deformation, you will have a flow coefficient in the end. So each eccentricity, or if you want, initial state anisotropy leads to a final state anisotropy because of the expansion which follows the pressure gradients. So this is always the same argument. So does it work in practice? So this is just one simple way to see that. The relation is that Vn is generated by an epsilon n, which means that I can look at collisions. For instance, if I'm looking at central collisions, I do many collisions. So each point in this plot is one collision event, and then I record the initial spatial anisotropy for the second and the third harmonic in each of these. And then I measure, I perform my hydrodynamic simulations with all the dynamics included, etc. I look at the final state elliptic flow and triangular flows, so n equal to and n equal 3. And I can see that epsilon 2 and epsilon 3 are perfectly, sorry, V2 and V3 are just in a linear correlation with the initial state anisotropy. So this includes all the expansion, the evolution, even something about the hadronic phase if you want. You see, you are assessing, this is the important guy for this. So initial conditions are very important, and that's what you see in the experimentals. There's something even more sophisticated that I can do if you want to follow me. If I again look at linear response, I can look for what are called multi-particle correlations. So more complicated observables, which are constructed from these flow coefficients. These are what they measure are basically cumulants of the distribution of V2. Which have these definitions. So there is this cumulant of V2, of V3, and then there is a mixed cumulant involving V2 and V3. So these are all observable quantities, and you can ask, okay, but what if I have an initial state model which gives me an epsilon? Can I actually reproduce these observables from just the initial geometry of the system? And you see that in general, so these are the data which was released by Atlas with very high precision measurements is these points. And in general, if you have a good initial state model, like the Trentum model, which I also discuss later, you just evaluate these right-hand sides, and you see up to 20% or even 30% centrality. You just capture the data quantitatively. Then the response becomes sort of more non-linear when you have high anisotropies at larger centralities, which means more peripheral collisions. This works pretty well. So this is what you're seeing in the data eventually. With these observables, you're just seeing the fluctuations of the geometry of the system, which is encoded by these epsilons. Any observable? Well, new observable, no, it's actually not a new, but something that has been realized recently. It's extremely powerful to play this kind of games. Is the question, the mean momentum precisely, which somehow answers the question is how much do you flow? So this is not about the shape of the flow, which is whether elliptical, triangular, or etc., but it's more like how strongly it flows. So the energy per particle tells you about that. You don't care about anisotropy here. It's just a mean value. So what does this quantity probe actually? To understand what the physical origin which drives, let's say the physics which drives the mean PT, it's actually very useful to look to think about a gas of particles in a given volume. So if you have an ideal gas of massless particles, the average momentum of the particles is just proportional to the temperature, which means the following: that and the entropy of the system is given by the number of particles. So in general, what you expect is that if you have two systems which have the same number of particles, or entropy, which in every collisions will be the same final state multiplicity, so the number of particles that you detect, if one of these two systems has a smaller volume, like A is smaller in size than B, then you are stuffing the same entropy in a smaller volume, which means that you're making the system sort of more dense, and the temperature increases. Then you expect to see a larger a momentum for the particles. Let's say if you release the container, things like this. So this actually is precisely what happens also in heavy ion collisions. And we can see it explicitly once again. This is very simple physics. But mean PT and the way it fluctuates is really about the thermodynamics of the system. You can play with some thermodynamic identities. And again, if you write an equation like this, and then if you again consider a sort of ideal classical gas approximation where mean PT, the average momentum is given by the temperature, you end up showing that relative fluctuation of mean PT would be positively correlated with the fluctuation in the energy of the system, because which of course relates to the temperature, and otherwise it's anti-correlated with the fluctuation in the size. So this is what I showed you here. The smaller size means a larger momentum. Now let's do again full hydrodynamic simulations of heavy ion collisions. We can fix the initial entropy, which is basically fixing the number of particles. And then you look at the distribution of mean PTs that you get in a large batch of events. And you can correlate it with the energy of the system and the radius of the system, or the measure of the size of the system. This is central lead-lead collisions. And you can see that mean PT, which again is a final state observable, is just sort of straight lines correlated perfectly with initial state properties. And you know, this has been demonstrated by several people actually, also in other calculations. What is interesting about this is that like energy is a quantity which let's say energy, size, all these sort of beyond energy and volume, thermodynamic quantities, they are circulated to the equation of state, which means that by looking at how the spread of this energy in the batch of collisions at fixed total entropy is about really the equation of state. So the slope of this line is telling you about the equation of state of the system, something we showed in this paper. So mean PT is about thermodynamic properties. Okay, so the anisotropic flow coefficients were about initial deformations. Mean PT is more about temperature and size. Now, how do you use mean PT to again create new probes of the initial state in the data? So a very powerful thing, which is now we will start to understand in more detail, is combining, in fact, mean PT, so this measure of the volume, with VN, with the anisotropy. So what the observable is a covariance, basically, which would be measured at a three-particle correlation experimentally, correlating what would be the V2. This is how you measure V2 and the average transverse momentum. It's something which has not been considered for many years. It actually appeared in this paper first as a sort of byproduct of the analysis they were doing. There was not really predictions for this. Then it was sort of written down in terms of a very straightforward thing that you would measure in experiments, so a real observable, multi-particle correlation observable, the way they would measure it experimentally by Piotr Boczek. This was in 2016. Okay, what was actually measured experimentally is a Pearson correlation coefficient between the anisotropic flow and the mean transverse momentum. So it's sort of correlating the anisotropy of the system with the size of the system. So this is the idea. Physically, this is exactly what it means. These are two. Let's see what does it mean to what this observable mean is really encoded in what the role of mean PT is, which means that you can take two QGPs. These are two initial conditions at the same final state multiplicity. Okay, this is n charge. So same entropy if you want, but then you take one as a very small mean transverse momentum than average, the other as a much larger one. So as I said, small mean PT means like lower density and larger volume, and large mean PT is more a denser system with smaller volumes. See here you see the effect of changing mean PT. So it's really a thing that plays with the geometry of the QGP, and it's clearly has a correlation with the epsilon2, which is the anisotropy of the system. As you move from this to this, you're changing. Actually, in this example, is the epsilon2 by a factor 2 essentially. which means that you expect some correlation between min PT and so this way of shrinking or expanding your system at fixed multiplicity with the V2, and this has been measured. This is observable, and then once again it shows that indeed these initial state arguments about anisotropy and system size related to Vn and MPT, they are correct in a sense, because we can again look at take our initial condition model and estimate from initial state quantities the outcome of the experiment. So this is what has been measured by Atlas. These are these points, and the initial state estimation is this red line. So you see the shape is captured, and quantitatively it sort of makes sense. Also for the collection V3 and MPT, this is also, you have the right order of magnitude, so it's also quantitatively consistent. There are effects which are not captured just by the initial state calculation, but it is pretty clear that what you're seeing is the initial state quantity. It's also a quantity that now has been checked sort of more explicitly. It's all these observables are in hydrodynamics very little dependent on viscous corrections and beam energy, which again emphasizes that what you're seeing when you do a measurement of this kind is more like the initial state. Okay. Sorry. Yes. So this was essentially the first part of my talk, just to show you that you can, in fact, understand final state observables in terms of initial state quantity. So an isotropic flow tells you how deformed you are, whether you have an elliptic, triangular deformations and things like this. If you have a round system, you will have small Vn coefficients and also small epsilon n coefficients. Min PT is a measure of system size, and if you want EOS, you can predict it very well with the energy of the system, for instance, at a given multiplicity. So small min PT is a system which is larger and not so dense. So there should be another plot here. I'm not sure why it's not true. Anyway, correlation of Vn with min PT. So you sort of couple these two things. You ask somehow, if I change the shape of the QGP, does it get also more or less anisotropic? If I make it more anisotropic, does it get more dense so that min PT goes up or down? This is the physics you're probing with these observables. And okay, sorry, that's not what yeah. So now that I sort of clarified the underlying physics, I want to show you. Let's go to what you can probe now with these observables in terms of initial state physics. So again, the problem to get to the QGP involves three ingredients mostly, which are what are you colliding? So it's nucleons, say nucleon constituents like quarks, gluons. What actually matters for the interaction? Then how does the interaction occur, and how the QGP phase is reached? Then with some something which will turn the initial out of equilibrium energy density into the QGP. So again, I don't have time to discuss all of this. Sorry. Okay, to discuss all of these points in the talk, so I will focus on recent insights coming mostly from these 2 points and involving these observables that I discussed about. Okay. So the first thing I have to somehow remind you is how we understand the nuclear collision in the models. So this is not, I'm not sure how much this is clear, but let me remind you that what you do is basically you have a nucleus which is boosted along some z-axis, which would be your beam axis, and then it becomes a sort of transverse, sort of projected object in the transverse plane, and you have to define some field, some density, which represents actually the thing that you are colliding. Okay, so you turn your nucleus from the rest frame, if you want, to a two-dimensional object which you will use in the collision. So it's typically something which looks like this. So this is actually a real model simulation. And then you will do the same for the second nucleus. And then there will be some way to combine the two nuclei to get you some initial profile. So this then is up to the model that you're doing, whether it is an energy density, an entropy density, a temperature. And so typically it's an energy density, or it can also be an entropy density. And this. Now, this operation here is something that we essentially don't know very well. What we have been able to establish is phenomenologically viable pictures. So the only somehow theory input that we have about what happens here is from the color glass condensate. There is one of the say more basic results that you get in the color glass condensate, and this idea of the plasma, this classical, the semi-classical approximation, is that the energy density at the initial time, right after the collision, is a product of the two TA and TB. So these are you will get this. In more recent times, the most popular one, so this is used, for instance, in the IP plasma initial condition model. What is mainly used, I would say, in the phenomenology, let's say, when you don't use this one, there's basically just one alternative, which is what the Trenzo ansatz, which is the one I used actually in the previous plots, where this Q exponent is 1/2. So it's the square root of the product of this. That will give you the energy per unit rapidity at the initial time. And this is something which has been essentially constrained from Bayesian inference of the experimental data. So this is basically what we have, okay? And what I will use. CGC is slightly different from Trento. There is no clear, let's say, I would say, we don't know at this point which one is better. This is something for the future, but these are the two ingredients. The point is, once you know how to combine these two objects to get your initial energy density, you have to create your TA or your nucleus, basically. And this is something which goes in 2 steps. So what actually the nucleus which is being boosted tells you is more like where the nucleons are. So this is a transverse projection of the actual positions of the nucleons inside this nucleus. And then this will get somehow smeared to obtain the nuclear density. And again, this is not something that, again, the only thing we can do is establishing phenomenologically viable pictures. What has been used, let's say from the start, very long time, is the idea of using a superposition of Gaussians. This is also what is used in IP plasma, very close to that. So on top of each of these coordinates of nucleons, you will put a Gaussian with some width, and then you superimpose them to get the TA of the nucleus, and then you know how to do the scattering. So this is the picture that we have, and it goes with 2 ingredients, which are the coordinates of the nucleons and the size of the nucleons. Okay, so let's say you need to know where the nucleons are, and then you need to know how big is the Gaussian. So this is pretty much this is the ingredients you need. And of course, it's sort of interesting then, because if you want to understand the details, you need to know where to take these things, which means that you need some input about the nucleon structure. So what would be a reasonable Gaussian to use for your nucleons, but also you need to know how to sample the nucleons, which their coordinates, which is a nuclear structure question. And these are the 2 things that I want to discuss here. How the NMPT correlations can help us, at least what we understand, can help us understand these two features. Okay, so I will first discuss about the nucleons, since there has been quite interesting progress on this. What has been used about the nuclear structure, if you want, from the very start of when we started doing Monte Carlo simulations of avian collisions, is the idea of doing Monte Carlo Glauber models, where you take some density, which is called Wood-Saxon profile for the ground state of your ions, and then you do a sampling of nucleons for each of the 2. According to this density, which is something that is typically taken from fits of low energy electron scattering on nuclei. So there are 2 parameters usually to describe the shape of your ion. So this picture where you do independent sampling of nucleons according to this ground state density it somehow worked amazingly well. Let me just give you an example. If you couple this with a model of energy deposition and then evolution, so this will be for instance IP plasma plus D. So I have some results here. If I compute the V2 and V3, which especially for central collisions are dominated by fluctuations in these nuclear positions, you see that the theoretical model actually produces the data extremely well. So it means that, and this is not with any special tuning, I would say. This is not even like a Bayesian analysis or something like that. This is just very naturally telling you that the fluctuations that you need to describe the anisotropic coefficients, for instance, are immediately captured by the Monte Carlo Glauber model. So this is a mean field approach, if you want, where you have independent nucleons in a common potential or common density, and it's really powerful. So what has been understood now, at least one thing that has to be added to this is the fact that there are strong correlations, strong correlations in nuclei, which are very collective objects, and which also display remarkable, collective phenomena, the emergent phenomena in nuclei. So one thing is, for instance, what is called deformation, which is one example of emergent phenomena in nuclei, for instance, what happens with when you have nuclei nucleus like uranium, where you have a spectrum for let's say the states of the nucleus, which follow this law, which is basically the standard quantum mechanics formula for the energy spectrum of a rigid rotor, so like a diatomic molecule or like a rod, an object which rotates around one point. And this is extremely accurate, actually. So it's very striking in a sense. It's been known, for a very long time. And it's the way it's understood it has been understood, and now it represents like the consistent picture of nuclei, is that you can indeed associate the notion of sort of shapes to these nuclei, and which are sort of like this. For instance, if you have an ellipsoid that rotates in space, and with some random orientation, and this allows you to describe this sort of phenomena very well. Microscopically, it's a complicated phenomenon. It's typically studied in Hartree-Fock theory, where you do minimizations of. You start with some nuclear Hamiltonian, and then look for let's say minimization of the energy to find the ground state with some constraint to see if your system prefers a sort of deformed geometry, and this is what is typically found for nuclei like uranium, for instance. I suppose microscopically it's a complicated phenomenon, but this is how you can effectively see it. In heavy-ion collisions, then we can see this as well. This is very natural because these intrinsic shapes, they are there in all everywhere in the phenomenology of nuclei. So now we are clearly seeing. We should expect to see them also in heavy-ion collisions. It means that you can generalize your Wood-Saxton by means of a spherical harmonic expansion of your sphere, if you want, which will involve an ellipsoidal deformation, which is typically called beta 2. So this is associated with the quadruple moment of your nuclear density. So it sort of gives it the shape. Plus, for the quadruple deformation, there's also an intrinsic parameter which is called gamma, which is called the triaxiality, which essentially tells you what is the imbalance in your ellipsoid of the three axes. A nucleus is gamma is a quantity which goes from 0 to 60 degrees, and you can have prolet or triaxial or oblate nuclei depending on the value of gamma. So prolet is 2 short axes and 1 long axis. Triaxial is 3 different axes, and oblate is 2 long axes and 1 short axis. So you have a sort of squeezed like planet Earth object. So this is clearly a sort of additional input to the modeling of the initial state of heavy-ion collisions, and it couples immediately with all the stuff I discussed at the beginning of the talk, because you expect that there will be, depending on how these shapes are oriented, you will probe different collision configurations, essentially, which will then reflect in the shape and temperature of the QGP. So if you have 2 extreme cases of collisions of deformed objects, so one would be like this. This will create a round system with a small V2, if you want. This is what is called a body-body collision. Will create an elliptical system like this. Oh, sorry. So this will have a larger V2 than this one. At the same time, you are looking at collisions at fixed multiplicity. This has more density than this one because it's contained in a small volume, which means that it has a larger mean PT and a smaller mean PT. So these 2 quantities between mean PT, they sort of allow you to somehow control the relative orientation of the colliding ions. So you can see this experimentally when again by studying V2 mean PT correlations. Again, for a small V2, you expect a large mean PT. For a large V2, you expect a small mean PT. So there is a negative correlation to these 2 quantities, which is then observed experimentally. they perform the uranium-uranium collisions, precisely the nucleus I've been discussing above. And in the limit of central events, where you sort of probe the entire shape of the nuclei, you see that this effect at play. So there is this bending of the observables towards these very negative values, which is consistent with this prediction. So now you have an observable which is really dominated by these intrinsic shapes and the way they are oriented, and it's an effect which you see is actually surviving across most of the centrality range. So you really need to be sure you know what you're colliding to understand this kind of experimental data, which is very nice, I think. There is one step further that one can do, again, by putting into the picture this parameter gamma, which tells you whether the nuclei are prolate or oblate. And the idea is really easy. Is that if you want to create a system with a large area, which would be a small min pt, then for prolate ions, which would be gamma equals 0, you need a collision like this. This is a large area of overlap, but it's also elliptical. You see, it's an elliptical area of overlap. If you have oblate ions, which look like this, if you want to create a large overlap area, then you have something circular. So depending on this value of this gamma parameter, which tells you whether you are oblate or prolate or in between, the low min pt events have a different geometry of their initial condition, and high min pt events is a similar story. And in fact, again, do we see this also at LHC? So the effect of this gamma parameter, in heavy-ion collisions. And yes, in fact, this is now seems pretty clear at Large Hadron Collider in particular, when they collided xenon isotopes. In fact, these isotopes, let's say, neighbors of 129 xenon, which is what has been collided at LHC, even isotopes which can be studied sort of accurately in low energy experiments, they're found to be triaxial, so they have this gamma parameter non-zero. And you would like to find the same feature in the LHC data, and actually this can be done. So the idea here in this plot is to study how the correlation between V2 and min-pt changes in xenon-xenon collisions with respect to a baseline of spherical nuclei. So the baseline is basically 1, which is what you would have for a spherical xenon nucleus. And then I did calculations where I have, again, in the Trento approximation, by using Trento estimates, where I use prolate nuclei, which is this line here, or oblate nuclei. So the effect of changing from prolate to oblate is precisely something like goes as expected. And also this was explained by Giuliano how this works quantitatively, I would say. The point is that the data, as you can see, sort of in the middle of the two cases, which somehow points, okay, but then is really, maybe already seeing this the fact that the nucleus is triaxial, which is in between prolate and oblate. This is then, I wanted to understand this, so I went to the actual people doing state-of-the-art calculation for large nuclei and say, can you actually compute 129 xenon? And so they did that. So this is, okay, I'm no nuclear structure expert, but this is the calculations are actually kind of interesting. These are sort of minimizations, again, like sort of Archifock, but done in two steps. First, you consider an independent Nucleon ansatz, and then you look for the ground state of the the minimum, say the ground state, so the minimum of the energy for different possible deformations, for different valuable deformations. Then you will shape in the beta, in the plane of deformations, which is beta and gamma parameters, a sort of energy potential map. And then you can actually enrich this by, let's do something better, in a sense, by taking superposition of the states that you obtain at all these deformations in what is called the beyond the mean field wave function, which is something which is now the symmetry is more consistent with the nuclear Hamiltonian. And so each deformation, if you want, contributes to the final wave function with some weight. And then you can do, again, your rational equation, solve again your rational equation to extract, again, the ground state, if you want. But you can also assess somehow a function which tells you what the probability of shapes is, or something close to that, which is what I show here. So they did that for 129 xenon. This is now published in this paper. And we found indeed that the shapes which matter for this nucleus are around the quadruple deformation of 0.2, which is what I used in the previous plot. And indeed, this gamma parameter is not 0.6, meaning that the nucleus is not like was here. It's not oblate and it's not prolate, but it's sort of in between. And so indeed, if you then do the calculation when the input from state-of-the-art nuclear theory, you end up on top of, very close to the ellipse measurement. Now Atlas will show the actual final results of this at Quark Matter in one month from now. So just to close this chapter, prospect here is, I think it's very remarkable. You can see this, you can play with this orientational shapes and see them in the collisions. So you can really somehow improve your modeling of nuclear collisions. And this is going to be relevant for all sorts of nuclear collisions. You need a consistent model of nuclei across scales. And this I think is very, very exciting. You can do low energy collisions like JEV scale. You can do electron-ion collisions. Intrinsic nuclear shapes will be there always. And so it's going to be exciting to explore this further. If you're interested in this, we are organizing, we have an approved program at INT at the beginning of next year. That's organizing. So the second thing then is the nucleons. Okay, now maybe I have a super accurate nuclear structure model which tells me how I should sample the nucleons. Then what do I do with these nucleons? Again, I need to turn them into something that I can use in the actual collisions. And then, again, there are not so many options in a sense. You have to either turn the nucleon into a smooth object, which will then fill your nucleus. So here you will need basically a nucleon size. This will be done again with Gaussian functions. Or more recently, people are using a subnucleon structure, which is a very interesting topic, of course. And there you add two other parameters, which are the number of constituents. In this case, you would turn your nucleon into 3 hotspots. And each one is associated with some size as well. So there's also a constituent size. So now, why is this topic, the topic of how this happens, has sort of been not really discussed much, I would say, in heavy ion collisions for many, many years. And let's just try to recall what has happened. Basically, as people realized that you had to do Monte Carlo Glauber model with the nucleons, then you had to introduce some sort of size. And I believe, at least for what I could read in the literature for almost 15 years, well, you say, okay, let's just use some reasonable size. We don't really care too much about it. Typically, it's sort of what has been used is 0.4 Fermi. I believe this, this is a sort of natural scale because it is between somehow 1 Fermi and what would be more like the saturation scale, which is more like 0.1 Fermi in high energy QCD. There is one paper, this is the only one I'm aware, where they actually quote some radius by means of by studying Gibbs-side photoproduction at Hera. They extract some size parameter. They call it the 2-gluon radius because it's sort of process dependent in a sense, depending on what they're studying. And this turns out to be, okay, the two-dimensional radius is 0.5 Fermi. So in simulation, so if you divide by square root of 2, you somehow get 0.4, which is consistent with this stuff. So this is the picture of the nucleons used in high energy event collisions for a long time, and no one really questioned whether that's good or not. Now, small systems arrived where you see a lot of flow there too and fluctuations, and so you need the subnucleon structure. And what has been realized in particular is that if in models like IP Glasma or even Trento scaling, you cannot describe proton-nucleus collisions, for instance, if this is your nucleon. Okay, you need some structure, additional structure, to make it more fluctuating. So in the context of small x physics, there were again studies of Gibbs-side production. This is sort of rather well-known picture of, for instance, a proton with 3 hotspots. These actually turn out to be very highly fluctuating protons. The size of this is like 0.1 Fermi associated with this. And indeed, this has been somehow this has come out. Let's say that it's important in the context of small systems, but now I want to argue that it's actually even important in large systems, which makes it opens a new direction in a sense. And the reason why I got concerned or interested in this is precisely that at some point I just wanted to make some order and see what kind of calculations were in the literature and what picture of the QGP we're getting out of those. And this is what I ended up with. It's shown in this plot. So these are all results from papers we have done Bayesian analysis of the soft sector data, if you want. This one is IP plasma initial conditions, the most recent one, which is not a Bayesian analysis, but as more ingredients from hydrogen theory. So what is striking here is how much these differ. You see, you really have a QGP, which goes from something which at the initial condition is very spiky and with local clusters, if you want, to something which is gradually smoother. So this is almost a bag of uniform energy density. You can see it that way. So then I wanted to somehow understand why are they so different, and it was sort of clear what is actually happening here is that what is being collided is very different. It's really a question of nucleons. There are differences in the way these energy densities are created, but what really matters for these plots is actually the size of the nucleons. So in IP plasma, again, you have a proton which is highly fluctuating with the 3 small hotspots, and the associated length scale is 0.1 Fermi, and this leads to these very spiky structures. Triactium is a framework which has done Bayesian analysis with the Trento model with substructure, and the size here is 0.5 Fermi for the constituents. So these are sort of pretty fat constituents in a sort of fat nucleon, and so it's a sort of, this is the picture you get. The Jetscape collaboration analysis, or like also what was done by the Duke group, they had a paper in Nature Physics, for instance, they don't have a subnuclear structure. They just fit the soft sector data, and they get as a result actually very large nucleons. The size associated is 1 Fermi, and this is why this profile is so smooth eventually. So in general, you see that whatever you get from the Bayesian analysis is sort of favoring smoother systems. And this is a sort of variance with what is implemented in IP plasma. So I will just do a very straightforward thing and say, okay, so what happens if you compute Vn, V2 min PT, and V3 min PT correlations in these models? So this is actually what happens. It's shown in this plot that if I take the 3 frameworks, so which again, IP plasma plus music, Triactium, which is Trento plus Hydro, and Jetscape, which is also Trento plus Hydro, just different initial states. You see that there is a completely remarkable difference between different state-of-the-art codes, and even codes that are essentially have done the Bayesian inference from the same set of experimental data. So this is what you get. You see, there are qualitative differences. Observable can turn negative even at low centrality in lead-lead collisions. And what we see is that the ordering of these curves follows precisely the ordering of the sizes of the nucleons which are implemented. So is this a coincidence, or are we actually seeing the size of the nucleons here? So to explore this, then I said, okay, we should be able to figure this out just by doing Trento simulations. So this is what has been done in this paper, which is now shown in this publication, which is also published in PRL. About doing Trento simulations with different nucleon sizes and looking at these observables. And precisely what I find is that depending on the size of this the nucleon, so which is really this ball, or this ball, there are again the same sort of qualitative differences that you have seen in the full hydro simulations. So let me just emphasize that this is completely non-trivial, because here we are talking about lead-lead collisions around 25%. So this is what you would really call a large system, where short range, if you want, structures or short scale should not really matter that much. But as I just increase the nucleon size, this turns from positive to negative. I mean, I have some experience with this kind of observables, and it's very difficult to, turn the sign of an observable in almost central lead-lead collisions. And so this is a completely new feature of the initial state variant collisions, in my opinion, and I don't really understand what is going on here. I will say something about it, but it's really unclear. But this is what it is. Then we asked, okay, do we see the same behavior in actual? So this was a Trento estimate. What if we do the full hydro calculations in the fully comprehensive framework? So we did calculations for different nucleon sizes. So this involves the full evolution with free equilibrium, QGP, hadronic phase, etc. Just changing nucleon size, you compute the same observables, and you see some of the same qualitative features happening, especially for the correlation with V3. you see that, again, 20–30% centrality, just changing the size of the nucleons is flipping the sign of the observables, observable. In the full hydro calculation. So again, what then we realize is that what you can see is that if you plot what has been measured experimentally, so I forgot to put the references to the experimental papers. I'm sorry about that. Is that there are no negative signs. There's no steep trend. This was explored very much detail by Alice. I think next week you have a talk by Yo Zhou from Alice, so he will show you what Alice has done on this, I'm sure. There are no steep trends in the data. There are no negative signs. So things are more consistent with the, if you want, the picture of IP plasma plus music than with the other two calculations. Although these are, state-of-the-art results from Bayesian inference, they are just inconsistent with the experimental data. And the one crucial role, which is clearly at play here, is the size of the nucleons. The current estimate of this sort of large, or fat nucleons that you get from the Bayesian analysis is not viable. You cannot describe these observables. Then we investigated. Somehow we wanted to ask, to answer the following question: what is the relevant length scale? Because for instance, in IP plasma plus music, in principle you have also the subnucleonic structure. So you can do your calculation with with smooth nucleons and different sizes, and this is again the trinity correlation. You have these trends I've described, but then you can do the Fourier calculation where you keep somehow the size of the nucleon the same here. So they found the nucleon in which you sample the hotspots as different sizes, but you keep the size of the hotspots the same. And then you see that here I kept 0.27 Fermi, just a random number. You see that these three lines then collapse into one. And this means that what is really important here is the size of the hotspots, of the constituent of the nucleon. So this means that this is somehow probing the relevant scale, which in this kind of processes you probe. The relevant scale that you probe in these processes, which is inside your hard disk, because eventually you know that the scattering occurs between constituents of the protons, and so that's you're really very sensitive to that size. Again, this was a trend to estimate. Then we also did the hydrodynamic calculation, where we precisely studied this. We take a very large nucleon with small, let's say, small constituents, and a much smaller nucleon with constituents of the same size. And this is this blue line and these symbols, and you see that the results are consistent essentially. So again, even in the full plasma plus QMD calculation, the observable is sensitive to the size of this nucleon constituents. And if you do, again, this is a calculation for one individual blob in your nucleon, and it's qualitatively different. So just turning from this to this, it's flipping the sign of the observable. So eventually you're somehow probing the structure of these nucleons, or if you want the fine scales, short scales in the nuclei that are colliding by means of this observable in a very effective way. What is not shown here, which we have also tested, is what if instead of 3 you have like 6 or 9 or a larger number. It's actually less sensitive to that. So there might be more than 3 hotspots. This was recently done again in a Bayesian analysis framework. I think they end up with 7 hotspots, but you wouldn't really see very much that here. So what this is probing is really the size of these constituents, not very much their numbers. So that's actually an interesting question to figure out how to also probe the number. It would be very interesting. So I have 2 slides left, if I can. Just in prospects on this. So what is happening here? So why are we so sensitive to these things? this again, I don't know. We just found this out. I think it's a nice result. I believe a way to approach this problem is to sort of look at the field itself, at how the fields fluctuate, which means that the energy density field is in general something like this in a gold collision. This is an example from one paper. Somehow a natural way to try to see how this fluctuates is by studying correlation functions. So this is, if you want, the connected two-point function of this field, which the average is over several events in a centrality class, for instance. And this is typically something that you can split into a part which depends some of the amplitude of the fluctuation and the correlation length. Okay, it depends on the distance between the points. I have to give credit again to the authors of this paper who decided to plot the two-point function of an energy density field for cold collisions. And indeed, there is a part related to nucleons and a part related to more like the nuclear structure. And eventually, if you think about this, then as soon as you have an observable in hadronic collisions which probes these scales, then it's natural that you can probe even the content of the nucleons and these short scales, because this is all encoded in this function. So this would be some either change in correlation length or renormalization, depending on what the content of your nucleons is. So this also sorry, somehow shows why it's very natural that in the hydrodynamic picture, it's easy to see these things, because there, once you have the hydrodynamic field, everything becomes very simple. It's just an expansion driven by pressure gradients. So as soon as you're sensitive to short scales, then you will just probe them very easily in the experimental data. So I think this is the direction to go to understand better, let's say, this kind of results, which just changing what's the constituent size or the structure of the hadron, you will change significantly your finite observables. A bonus, I think the size of nucleons, which we have to understand better. We have to figure out why these Bayesian analysis frameworks are returning such smooth geometries. Is intrinsically related to the question of the bulk viscosity in the quark-gluon plasma. So not much is known about the bulk viscosity, except the following, that it affects the observables. And again, the role of it depends a bit on the initial state. Let me try to explain what I mean here is that if you have something like this, which is a system which is sort of sharp, this will have very large energy density gradients and a very large radial flow. The mean PT is typically gets enhanced by the smaller system size. Okay, this is stuff we discussed at the beginning. Here you have a smoother system, you will develop less radial flow because of smaller gradients. So this really depends on what is the relevant length scale. But as a consequence, if here you produce too much radial flow, then you need the bulk viscosity, which will tame it, reduce it, and such that you will get the hadron spectra, which will match the data. This has been discussed very extensively in the context of philosophy of music, in the sense that they need the bulk viscosity, otherwise they will underestimate the mean transverse momentum. Conversely, these more Bayesian frameworks, especially the recent ones, they have very consistently returned very small values for the bulk viscosity, typically several factors smaller than what is implemented here. If you want, it's the temperature dependent, but the peak would be somewhere here or even smaller. So in the trajectory framework, for instance, I was quite impressed to see that the mean PT, again, which is a radial flow, is described perfectly well without a bulk viscosity, or like the value is something like 0.0, at the peak is 0.005 or something which you would barely see in this plot. The nucleon size parameter here is important. Therefore, understanding, for instance, these observables, what Atlas and Alice have measured, and gauging in this way the right nucleon size is going to tell you whether you want a bulk viscosity or not. Also, this is something to follow up. So I hope I'm on time. Let me just remind you, then conclude. Initial state of QGP can be probed experimentally because geometric and thermodynamic properties are clearly seen in final state observables. The mean PT correlations one example of such observables that are just really excellent probes of the initial state and the fluctuations, and they're affected in a very non-trivial way. And you can use them to probe nuclei and nucleons in ions and hadrons, if you want, in your collisions. And I've shown you how you can probe the collective structure of nuclei. So you can really probe stuff that for which you need state-of-the-art input from nuclear structure theory to understand this collective flow data and central collisions. The point of triaccelerator for Hydrodynamic xenon, and they have a remarkable sensitivity to short scales, especially correlation between V3 and min PT. The experimental data is not favoring a large nucleon size. A small size, I believe, is favored, and there will be more about this in the future. So, okay, this is what I wanted to say, and thank you for listening.
Well, thank you for Giuliano for this very comprehensive review of this topic. So now we can open for comments and questions. Yeah, please raise your hand or just unmute your mic and speak directly. So maybe while I'm waiting for people to gather their question, I have a couple of questions. One minor thing is if you go to your slide 27, and there is this centrality dependence of V2, and is this right? I mean, the Anaesthetic really have this very fine centrality beams?
Yes. Yes,
wow.
They measured in 1% beams. Yeah.
I see.
I don't have the reference. Oh, sorry, I didn't put the reference. Is run 2 data? I think it was shown right after Quark Matter 2018. I don't think it's the full run 2 data actually, but they are able to do 1% beams, and Atlas and CMS can do even better if you want.
I see. Okay. Well, I hope they can also look at other observables with this finer, very fine centrality beams, in addition to the just elliptic flow.
In LED, in future they can do that for sure.
So this is another question generally. If you go back to your page 40, for example, you talk about different. You're talking about different, like cluster, smaller and the sort of like structure inside a nucleon, right? And then whether they are small or bigger. But this is, I mean, if your final analysis conclude that you need some kind of smaller or big size of nucleon fluctuation, for example, that does not really mean that that's the fluctuation that you have as soon as you have the initially energy deposit, because there could also be the starting, it's just the size of the initial, fluctuation at the time of you match to the hydro, right? Or do you?
This is before that actually.
This is even before you start hydro.
This is 0+. It's really before you start. It's when you start the pre-equilibrium phase. So yeah, there will be a time scale which will be related to when you match to hydro. So this will change depending on that, because whether you sort of free stream more or less, then will change the structures too. But here, what I'm comparing is sort of equal time profiles, and they're all before any dynamics essentially. So this is really the initial condition.
But when you actually finally you calculate, you map into this V2 versus PT correlation, for example, or V3, that is you really have to go through the hydro in order to map your initial condition to the final observable.
No. So I mean, you certainly want to do that, but you can understand most of them just from initial state calculations. So I've done, for instance, I've done it, for instance, for this okay. This will be shown. This again in the Alice paper, for instance, because I did all these sort of these tests for all the different hydro models. You can see that you can sort of, so here I'm comparing the model, the initial state calculation with the data. So I capture it pretty well, but you could also look at these ones, which are the actual final state hydrodynamic results. And if you compute the initial state estimator, just from initial state quantities, it will be very close to these curves. And actually, qualitative, it will precisely capture all these qualitative features, like it will be less negative here, more negative for the jetscape initial conditions. It will follow very closely these curves, actually. So what really matters is these initial conditions eventually.
Well, in this case, I understand that your relationship between V2 and the geometric fluctuation, that is you have this sort of linear correlation that is understandable, but as for PT, I don't know whether you can relate to the initial cluster size without doing any hydro work.
This is what I showed here. You can do this. This is a calculation, a full hydro calculation of min PT for a batch of events. And it's if you then, so this is the final state observable, okay? And then you can match it to initial state quantities. So this is the energy at the initial condition and the radius at the initial condition. And you can see that these are again straight lines. So the final state observable is just determined by the fluctuation of the initial state quantity, even for the min PT. This is somehow
and this is I assume that when you change the size, this is under the condition the total entropy is the same, or is it?
Precisely, yeah, your fixed multiplicity, yes.
So okay, so you have to fix the total multiplicity.
Yeah, which is what they do experimentally. If you do for instance, what you said, a very small centrality beam. So these results will be pretty much at fixed initial entropy or final multiplicity. If you do very fine beams, then you can play these games with the min PT. Yeah.
Well, then this is another question. Is this this proportionality? The size versus PT. They should also, as you argued, they should also be sensitive to the equation of state, right?
Yeah, precisely. Because you can see it this way. I mean, it's really straightforward in the sense that you can have an entropy field which integrates to the same value, but it's still fluctuating event to event. So you have several entropy fields which integrates all to the same value. So this would be different QGPs, which leads to the same final multiplicities because they all have the same entropy. But since the equation of state is a nonlinear function, so entropy to energy is a nonlinear function, even if you're precisely fixed entropy, like in this plot, there's still a distribution of energies, and the spread of this distribution is dictated by the equation of state. And so the fluctuations of min PT, they depend on let's say how nonlinear the relation between entropy and energy is, indeed.
Yeah. And you I guess you have not really checked, if you change the equation state, how it will look like, right?
Not in this kind of calculation, not yet at least. But this is something that I should do. Thanks. We did it in a simplified framework.
That is interesting. Yeah, that is interesting because as you said in the beginning, this could have some kind of constraint on equation of state, and maybe
from the min PT fluctuations, I think you would get them really wrong if you had a completely wrong equation of state, for instance. Now people, they don't really change, if you do like the Bayesian analysis or things like this, you don't really constrain the equation of state from the data.
No, all the Bayesian analysis, they are all using a fixed equation of state already.
Exactly. Yeah. So in principle, you would see significant differences in like min PT fluctuations. Even just the value of min PT would be, or the shape of the spectra wouldn't be the same. This is all, governed by the equation of state.
Yeah.
This is how min PT works.
Okay, I just want to ask the audience, do you anybody have any other question, comments for Giuliano?
I just have
Okay.
one.
Yeah.
Yeah. So it's
Go.
just I'm just curious. On one of the slides, you showed that there's two overlap regions with fixed number of charge particles. Could you? Oh, yeah, this one.
This one?
Yeah. I'm just curious. What's NS in on the table on the right?
Sorry, it was there from another paper. Is the number of spectator nucleons?
Oh, okay.
It's the number. Yeah, the spectator. It's yeah. The nucleons which do not participate in the collision,
Yeah.
it depends quite dramatically on this mean PT actually.
Right.
Sorry, I could have removed that.
Okay, I think if there's no further question, let's thank Giuliano again. And it's very late in France. I think it's also time for you to rest. Okay,
Yeah.
thank you again.
Yeah, thank you very much.